Hello everyone. Today we're going to learn about intermolecular forces. Intermolecular forces, also known as IMFs or interparticle forces, are a collection of forces that exist between neighboring molecules or particles. IMFs are the microscopic forces that help hold together the macroscopic structures that we see in our everyday life. So, how do IMFs work? A reminder that charged particles have a coulombic force between them. If the charges are similar, it is a repulsive force, and if they are opposite, it is an attractive force. Atoms and molecules are made of charged particles. If you think about it, there either are ions involved, or if you break it down even further, there are protons and electrons involved. And these particles are always in random motion. And sometimes, especially in the case of polar covalent molecules, they are not evenly shared. Therefore, there are coulombic forces that can exist between molecules. Some of these forces are permanent and others are non-permanent. We will discuss the three main intermolecular forces now. The first of these, that kind of gives us a basic guideline of how these are going to work, is known as the dipole-dipole interaction. This is an intermolecular force that only occurs in polar molecules. What happens is, in the polar molecule, there is a dipole, a separation of charge that is permanent. It is not a full separation like it would be for ions, rather it is a partial one. And so, the partial negative of one end of a molecule will be attracted to the partial positive of a neighboring molecule, and vice versa. This is shown on the diagram below using simple, what looks like bar magnets to help represent the attraction between the positive and negative. Hydrogen bonding is another of the three main intermolecular forces. This is actually a special case of the dipole-dipole interaction. It occurs in polar molecules where there is a hydrogen that is bonded to nitrogen, oxygen, or fluorine, atomic numbers 7, 8, and 9. This acts exactly like the dipole-dipole interaction, where the partial positive attracts the partial negative. The thing that separates this is that it is unusually strong due to the fact that there is a very large electronegativity difference between hydrogen and nitrogen, oxygen, or fluorine. And this results in an unusually large dipole moment, which means there is a greater charge. A higher charge means a stronger attractive force per Coulomb's law. It is also of note here that the atoms involved are small, so you can also make hydrogen bonding usually act over much shorter distances, which would also help. However, this is more of a secondary effect for this one. Our third main category of intermolecular forces are London dispersion forces, also known as van der Waals forces. They are a temporary dipole-dipole interaction. They are non-permanent. London dispersion forces are found in all molecules and atoms. What happens is the electrons will randomly shift to one side, just due to the random nature in which they move, which is known as Brownian motion. And as a result, there is a temporary partial negative on one side where the electrons are, and a partial positive on the other where the electrons are not located. This results in there being the partial negative and partial positive like a dipole. It is again temporary. It'll eventually go randomly move, and so they will not be there anymore. But for the moment where it exists, you will temporarily have a dipole-dipole interaction, where the partial positive will attract a partial negative on a neighboring atom or molecule. It is important to be able to identify what kind of intermolecular forces an atom or molecule will have, because this will help predict certain properties, such as boiling point or melting point. So, in order to identify IMFs, there are two primary questions you should ask yourself. The first one is the molecule in question polar or nonpolar? If the molecule is nonpolar, there are only London dispersion forces. It is only capable of having those temporary dipole-dipole interactions. And so you have already answered the question. Nonpolar only have London dispersion forces. If you answer polar to this question, there is a second question you must ask yourself. The second question is, does this polar molecule have a hydrogen that is bonded to nitrogen, oxygen, or fluorine? If that is not present, then you have both London dispersion forces and a dipole-dipole interaction, since this is a polar molecule. If you answer yes to this question, then you have all three of the primary intermolecular forces: London dispersion forces, dipole-dipole interactions, and hydrogen bonding. So let's take a look at some example molecules. Determine the intermolecular forces present for the following: carbon dioxide, water, and nitrogen trichloride. You may want to construct Lewis structures in order to help you determine if these molecules are polar. Carbon dioxide is a non-polar molecule. It is linear shaped with the oxygens on opposite side. Therefore, since it is nonpolar, carbon dioxide only has London dispersion forces. Water is a polar molecule and is one of the more notorious for hydrogen bonding because of the O bonded to the H, not only once, but twice in the molecule, creating two different sites for it. So water has hydrogen bonding, dipole-dipole interaction because it is polar, and London dispersion forces. Nitrogen trichloride is a polar molecule. There is a lone pair on the nitrogen that has nothing opposite it to balance it out. But it does not have hydrogen bonded to nitrogen, oxygen, or fluorine. In fact, there are no hydrogens present in this molecule at all. And thus, nitrogen trichloride only has dipole-dipole interactions and London dispersion forces. Please notice all three of these have London dispersion forces. They play a role regardless of whether you are polar or nonpolar.